Here we are again, electromagnetic induction. In the past podcasts, we've kind of set the groundwork for talking about this. We've mentioned about needing and having magnetism when you have electricity. They're, as I have written up here, intertwined. It's like two sides of the same coin. You can't have one without the other. So, a moving charge creates magnetism, and it stands to reason that if you have magnetism, you can make a charge move. Think back to our little skateboarder, right? The skateboarder going across those grooves. When you hit the grooves, the skateboarder moved, deflected. And from this, we have the basis of most of the technology that we've created. So, if you look in my little picture here, at the top, we have a nice magnet, North Pole and South Pole. Remember, outside a magnet, the field goes from north to south. We have a wire cutting across perpendicular. And it turns out, as the charges move through that field, because they're moving perpendicular, they're going to deflect. They're going to be caused to go one way or the other. And we use, basically, another form of the right-hand rule for this. But anyways, this deflection is the basis of things like speakers, right? How else do we get the diaphragm inside the speaker to move? Well, those wires are being deflected because the charges inside them are being deflected. And the meters that we use to measure stuff, motors, generators, all that stuff uses this idea. In fact, without this, you wouldn't be watching this podcast now. That right-hand rule I was talking about, remember, it is called the right-hand rule. You need to use your right hand. The fingertips still represent the direction of the field. Your thumb still represents the direction of the current. The only thing we're adding is, coming out of your palms, like a superhero, is a force. So that's the force of deflection. Let's give it a try. Take your hand, make your fingers point in the direction of the magnetic field. And remember, which way does the magnetic field go? Outside of a magnet? North to south. So your fingers need to point up. And your thumb needs to go in the direction of the current. So you need to flip it so your thumb is pointing to the left. And your palm is pointing, therefore, inward, away from you, into the screen. And that's how you use the right-hand rule. You can determine which way it deflects. Well, a gentleman by the name of Faraday, who had a very rough life at first, as he wasn't a scholar but he aspired to be, he discovered something quite remarkable. He realized that you would get more voltage if you increase the number of loops of a wire, or the rate at which you move that magnet, or if you increase the strength of the magnet. This was a pretty amazing idea, because that is the basis of creating generators so we can produce electricity. However, a fundamental law of economics, of science, of life in general is something called Tanstaffel. There's no such thing as a free lunch. If you want to produce more voltage, you need to do more work. It's going to take more work. It's going to be harder to move that magnet in and out of the coil. It's going to be harder to move those electrons. So if you want to produce more voltage, yeah, stronger magnet, good. More loop, good. Faster motion, but it's going to require you more work to do it. So keeping this right-hand rule in mind, you can take the same device, and depending upon what you're putting into it, you're going to get the opposite out. In the case of a motor, if you put electricity in, you're going to get motion out. It's a motor. The opposite is true, or if you make it go the other way, you can generate electricity. Look, electricity in. If you want electricity out, you got to put motion in. Because it doesn't matter how you cause those charges to cut across the magnetic field, whether you move it or whether you send the electrons moving. The result is the same. So as I mentioned, this is the basis of all our electricity. If you watch my animation, think about what's going on. Right? It's alternating. Look at the direction of what's going on here. Watch. Right? As this cuts through this, there's a magnetic field going across here. Okay? Notice what's going on. It's being forced to cut through, and those electrons are forced to move, deflect. Over here, on this side, the current is moving this way. But when it comes on the other side, remember, it's following around. It's moving the opposite direction. The current is alternating. How about that? That's why we get alternating current. Anyways, if you want to review over this magnetism stuff, you might want to check out this website. It gives you a little quiz and gives you the answers. You can check how well you're doing.